Review, analysis of particle motion. Our objective for today is to analyze the motion of a particle by using calculus and a graphing calculator, and we'll look at a free response question from the 2003 Calculus AB exam. Now, this is number 2. It's a graphing calculator problem. A particle moves along the x-axis so that its velocity at time t is given by this function v of t is equal to -1 times t plus 1 times sine of t squared over 2. We also know that at time is equal to 0, the particle is at position x is equal to 1. So I've drawn the x-axis here, and we start with the particle at this location at t is equal to 0. And we have some questions about the motion of this particle. So let's read the questions. The first question is, find the acceleration of the particle at time is equal to 2. Is the speed of the particle increasing at 2, y or y not? So this is a graphing calculator problem, and here's what we have learned in our course. We've learned that if you have the velocity function, the acceleration function is the first derivative of the velocity function. So if we want to find the acceleration of the particle at time is equal to 2, we have to evaluate the derivative of the velocity function at time is equal to 2. But notice that we are not actually asked to find the acceleration function. We're only asked to evaluate the acceleration function at time is equal to 2. And since this is a graphing calculator problem, you should go ahead and enter the velocity function into your graphing calculator, and you can ask your calculator to find the derivative of the velocity function at time is equal to 2, and that would be the acceleration at 2. So the way you do that is you go to the math key, which is underneath the alpha key, and then you go to n derive, and you can have this pop up on your screen. Enter the function, and you want to evaluate it at time is equal to 2, and it will tell you the acceleration. Alternatively, you may enter the velocity function into y equals as y sub 1, and then go to math, go to n derive, and go to variables, y variables, function, and y sub 1. So once you enter the function once into y equals, you can access it so you don't have to keep typing it again and again. And then evaluate at x is equal to 2, and you get the same answer. Again, how do you do this? Enter the function once into y equals, and then you get the derivative by going to math, and then n derive, and if you want to refer to a function that's already stored in your calculator, you go to VARS. That key is somewhere over here, a little bit below what you can see on screen. And you go to y variables, function, and choose where you stored the function. The next part of the question is the speed of the particle increasing at time is equal to 2, y or y not? And here's what you need to understand conceptually. I'm purposely drawing a green axis because I'm speaking conceptually and not just about this one particular problem that we're looking at. But let's say you have a particle and it's over here at one point in time. If it's moving to the right, the velocity would be positive. However, if there is a force that's acting opposite the direction of motion, because the force is opposite the direction of motion, the acceleration would be negative. And you can see that if you push an object opposite the direction in which it's moving, it will slow down. On the other hand, suppose that acceleration is also positive. So acceleration would be positive. And if you push an object in the direction that it's already moving in, it will go faster. So here's what you need to understand. When velocity and acceleration have opposite signs, the object would slow down. When velocity and acceleration have the same sign, the object would speed up. So if velocity and acceleration are both positive, or if velocity and acceleration are both negative, the object would speed up. If they have different signs, the object would slow down. So from the first part of the problem, we know the acceleration of the particle is a positive value at time is equal to 2. And then you can find the velocity by evaluating the velocity function using your calculator at time is equal to 2, and you find that it's a negative value. And since velocity and acceleration have opposite signs at t is equal to 2, the object would be slowing down. The speed of the particle is decreasing at time is equal to 2. Now we go on to part B. Find all the times t in the open interval from 0 to 3 when the particle changes direction. Justify your answer. So what we can do is we can enter our velocity function into y equals. You may have already done that in part A. And then you can look at the graph of the velocity function for time values from 0 to 3. So I set the window settings from x is equal to 0 to x is equal to 3. And I set the window settings for y from -4 to +4. The reason I did that was because I know the range of the sine function is from -1 to +1. And then I'm multiplying by this factor, -1 times t plus 1. And the maximum value that I have for t is 3. 3 plus 1 is 4. -1 times 4 is -4. And if you multiply the sine function by -4, the range of your velocity function will be from -4 to +4. So I have my window settings. I'm looking at the graph of the velocity function. Here's the graph of the velocity function. And you can see that we have the x-axis here. And a portion of the graph is below the x-axis. So if you have a portion of your graph below the x-axis, that means the y values, which in this case represent velocity, are negative. So on this portion of the graph, the velocity is negative, and we know that when the velocity is negative, the object is moving towards the left. And on this portion of the graph, the velocity is positive, and we know when the velocity is positive, the object is moving to the right. So at what time will the direction of the object change? The direction of the object will change here, where the velocity graph intercepts the x-axis. And how can we find that? We can use our calculator. The way you do that is you do second, calculate 0, and then the calculator will ask you for a left bound and a right bound. So you're going to use your left and right arrows to move the cursor. Choose your left bound, press enter. Choose your right bound, press enter. It will ask you for a guess. Again, use your arrow keys to move the cursor to about where you see the x-intercept and press enter. And it will give you the x-intercept of the velocity graph, which is about 2.507. So at that time, the direction of the particle will change. Before that, it was moving towards the left, and then it will stop momentarily at that time because the velocity is 0, and then after that time it will move to the right because the velocity is positive. So now we look at part C. In part C, we have find the total distance traveled by the particle from time is equal to 0 until time is equal to 3. So we know that the particle starts at x is equal to 1 at time is equal to 0. And from the graph that we looked at for part B, we know that because the velocity is negative from 0 to about 2.5 seconds, more specifically 2.5066283 seconds, on that interval, the particle is moving towards the left because the velocity is negative. And then After that, until 3 seconds, the velocity is positive, so the particle turns around and moves towards the right. The question is, find the total distance traveled by the particle from time is equal to 0 to time is equal to 3. You have to be aware that because the direction of the particle's movement is changing, if you just take the definite integral of the velocity function from time is equal to 0 to time is equal to 3, we learned yesterday when we were reviewing applications of the fundamental theorem of calculus that this would give us the antiderivative of velocity as position, the position function evaluated at 3, minus the position function evaluated at 0. Now, in a situation where you have a change of direction, as we have in this problem, this will not give you the total distance traveled. Instead, it will give you the net change in position of the particle between those two times. In other words, it will give you the net change. After the particle has stopped at time is equal to 3, compare its position to the position of the particle at time is equal to 0. What is the net change in that position? That's what this will give you, not the total distance. When will this give you the total distance? If there is no change in direction, it will give you the total distance. So if you want to find the total distance, there are a couple of ways you can deal with that. One way is to go ahead and find the distance traveled by the particle as it is moving towards the left. When you evaluate this definite integral, it will actually come up, the answer will be a negative value, but you have to change that to positive. And then add to that the distance the particle is moving to the right. So again, you have to change the answer from this definite integral, which will be negative because the particle is moving to the left, change that to its absolute value, and then add to that the distance the particle is moving to the right. So the distance the particle moves left plus the distance the particle moves right is the total distance. The faster way of doing this is to go ahead and just say, well, I'm taking the absolute value of what I get from here anyhow, so let me just go ahead and make the integrand the absolute value of the velocity function. And when you do that and you take the definite integral from 0 to 3, it will give you the total distance traveled by the particle. The way you can do that on your graphing calculator is you go to Math, and you go down to FNINT. This will pop up on your screen. Enter the limits of integration, and if you want to do absolute value, you go to Math, and then you go to Number and ABS, absolute value, and then you can either type in your function or you can access the function that you've typed into y sub 1. And what we have for part D is, during the time interval from 0 to 3 seconds, what is the greatest distance between the particle and the origin? Show the work that leads to your answer. So we go back to the very beginning. At time is equal to 0, the position of the particle is here at x is equal to 1. We go back to the work that we did in part B, where we looked at the graph of the velocity function. You'll remember that the graph was something like this. So here's what we can see. At first, the velocity is negative, so that means the object is moving towards the left. And then the velocity is 0, so the object stops momentarily, and then it turns around and moves towards the right. So we know the position of the object at time is equal to 0. It's given at the beginning of the problem. We can find the position of the object at time is equal to 2.5066283. That's when the object changes direction, to see how much it moved towards the left. And then we can find the position of the object at time is equal to 3 and see where it ends up after 3 seconds. And then we can compare those three positions to answer the question. What is the greatest distance between the particle and the origin? So we already know where the particle is at the beginning. And to find where the particle ends up at time is equal to 2.507 seconds, we can take the definite integral of the velocity function from 0 to 2.507 seconds, and using our fundamental theorem of calculus, this is what we have. We know the position at time is equal to 0. We can solve for the position at time is equal to 2.507. And we use our graphing calculator, and we find that at 2.507 seconds, the position of the particle is negative 2.265. So it's a little bit further than what I drew on my diagram earlier. So if I wanted to make it accurate, I'd draw it a little bit more towards the left. And then it stops and it turns around. What is the position of the particle at time is equal to 3? Again, if I want just the position of the particle at time is equal to 3, I can take the definite integral of the velocity function from 0 to 3 seconds using the fundamental theorem of calculus. I know it's the position at 3 minus the position at 0. I can solve for the position at 3 seconds using my graphing calculator, and this is what I get. So if I wanted to make my drawing accurate, here's what I would do. I would see that the object actually stops at about negative 1.197, which is about right here. So this is about where the object goes towards the left, and it stops there, and then it turns around and goes towards the right. So at what time is the object furthest from the origin? At the time it stops and changes direction. You can see that on my drawing here. And how far is the object from the origin at that time? It would be the absolute value of what we have here. It is, in fact, about 2.265 units to the left of the origin. So in this lesson, we looked at a problem and we analyzed the motion of a particle by using calculus and a graphing calculator.